Ready for a deep dive? We're going to be looking at how our brains work.
Ooh, sounds interesting.
And trust me, this is not going to be your typical biology lesson.
All right.
We're exploring excerpts from On Intelligence
Yeah.
by Jeff Hawkins,
Okay.
who has, well, a pretty revolutionary theory about how we think.
Uh-oh.
Get this.
Okay.
He says our brains aren't computers,
Mm-mm.
but rather incredibly complex memory systems built for, get this, predicting the future.
Whoa.
Curious.
Definitely. I know I am. So what makes Hawkins's work so compelling is that he's not just a theorist.
Yeah.
He's an engineer who spent years trying to build intelligent machines.
Yeah.
And he hit a wall with the classic AI approach.
Uh-oh.
And came to a pretty radical realization.
What that?
Computers, even super powerful ones, are missing a key ingredient that brains have.
Oh, okay.
A memory system designed for prediction.
So it's like he was trying to bake a cake without flour.
Yeah, that's a great analogy.
You had all the other ingredients,
Right.
the processing power, the algorithms.
It just wasn't coming together.
Interesting.
And that missing ingredient, well, that led him to completely rethink how we understand intelligence.
I see.
He argues that the brain, specifically the neocortex,
Okay.
is a memory system,
Okay.
but one with some pretty unique properties.
All right, let's break this down.
Okay.
What are these special properties that make the brain's memory system so different?
Well, Hawkins highlights 3 key properties:
Okay.
storing sequences, auto-associative recall, and invariant representations.
Okay, lots of big words there.
Yeah.
Let's start with sequences.
Okay, so you probably don't realize it, but
Yeah.
your brain is constantly recording sequences of events.
Really?
Yeah, like imagine you're walking through your house.
Okay.
Your brain remembers the order of the rooms, the feel of the floor, the sounds you hear. The neocortex stores all of these experiences,
Okay.
not just as isolated snapshots, but as a continuous flow of events.
So my brain is like recording everything like a video camera.
Well, not exactly a video camera, more
Yeah.
like a symphony with all these different instruments playing together,
Interesting.
creating a unique and constantly changing melody.
I like that analogy.
Yeah.
It makes sense. We experience life as a series of moments, so it seems pretty logical that our brains would store memories that way too.
Right, exactly.
But what about this auto-associative recall?
Yeah.
That sounds pretty complex.
It is. It's a fancy way of saying that a small piece of a memory can trigger the whole thing.
Well.
Yeah, think about a time when you smelled something familiar, maybe freshly baked cookies, and it instantly transported you back to your childhood.
Oh, yeah.
That's it. A single sensory input sparked a cascade of memories, sights, sounds, emotions,
Wow. Yeah.
all linked together.
That's so true.
It's like those moments when a song comes on the radio
Yes.
and you're suddenly flooded with memories from a specific time and place.
That's exactly what I was thinking about.
Yeah.
Exactly.
So powerful how just a single note
Right.
or a few words can unlock an entire experience stored in my brain.
Yeah. And this brings us to the third property,
Okay.
invariant representations.
Another big word.
Basically, it's how your brain recognizes things even when they change appearance.
Give me an example.
Sure, you can recognize a friend's fakes from different angles, in different lighting,
Okay.
even with a new haircut.
That's true.
So it's like your brain isn't just storing a static picture of your friend's face. It's building a flexible, dynamic model
Okay.
that can adapt to different situations.
So it's more like a 3D model that can rotate and morph.
That's the idea. It's not about matching pixel for pixel.
Right.
It's about understanding the essential features, invariant properties that define that face.
This is a key difference between how brains and computers process information, right?
That's right.
Computers are great at matching exact patterns,
Exactly.
but they struggle when things change even slightly.
Yeah, they're not very flexible. This is fascinating. So if the brain isn't just a number-crunching computer,
Yeah.
what is it doing with all this memory? What's the point of storing all these sequences and invariant representations?
Well, Hawkins says the brain is using its memory to constantly predict the future.
Hold on.
Yeah.
My brain is predicting the future.
In a way, yes.
I don't have any precognitive powers that I'm aware of.
Well, it's not about seeing into the future.
Okay.
It's about anticipating what's most likely to happen based on your past experiences. Think about something simple, like walking through a door.
Okay.
You don't consciously calculate the width of the door
Right.
or the angle you need to turn your body.
Yeah, don't.
Your brain has done this so many times before that it automatically predicts what needs to happen and adjusts your movements accordingly.
That makes sense. It's like My body just knows what to do without me thinking about it.
Exactly.
So it's not about conscious thought.
Right.
It's about these unconscious predictions guiding my actions.
Precisely. And these predictions aren't limited to simple physical actions.
Oh, really?
They happen at all levels of brain activity.
Wow.
Like right now, as you're listening to me,
Yeah.
your brain is predicting the next words I'm going to say,
Really?
the next ideas I'm going to present, based on its experience with language and conversation.
That's wild. So my brain is always one step ahead,
Yeah, you could say that.
trying to anticipate what's coming next.
Exactly. And this constant prediction is what makes the brain so efficient.
How so?
Well, it doesn't have to process every single piece of incoming information from scratch.
Okay.
It can anticipate what's coming
Right.
and focus on the things that are unexpected or surprising.
It's pretty amazing.
It is. It's like having an internal autopilot that helps us navigate the world effortlessly.
But if our brains are so good at prediction, why do we still make mistakes?
Well, that's a good question.
Why are we sometimes surprised by things?
Because the world is a complex
Yeah.
and ever-changing place. Our predictions are based on our past experiences.
Right.
And sometimes those experiences don't perfectly match the current situation.
That's true.
But even when we're wrong, our brains are incredibly quick at learning from those mistakes
Okay.
and updating our internal models.
So we're constantly learning and refining our predictions.
Exactly. It's a never-ending process of adaptation.
That's really cool.
It is.
Anyway.
It's one of the things that makes the brain so remarkable.
So I'm starting to see how this memory prediction framework really changes how we think about intelligence.
It does. It's a whole new perspective.
But it also raises a lot of questions.
Oh, of course.
Like, if all this prediction is happening unconsciously,
Yeah,
where does conscious thought fit in?
that's a great question.
And one that I hope we'll delve into further
Absolutely.
as we explore Hawkins' ideas.
We will, but first, let's talk about how this memory system is actually structured.
Oh, good point. It can't just be one big jumbled mess of information, right?
Right.
There has to be some kind of organization.
Exactly. And there is. The neocortex, the part of the brain responsible for higher level thinking,
Right.
has a hierarchical structure.
Okay.
It's not just one big memory bank, but a series of interconnected levels,
Okay.
each building upon the one below it.
So like a pyramid,
Exactly, like a big...
with the most basic information at the bottom
Uh-huh.
and the most complex understanding at the top.
That's a good analogy.
That's like building a house.
Yeah.
You start with the basic building blocks,
Right.
like bricks and wood,
Uh-huh.
and then you use those to create walls, rooms,
Yes.
and eventually the whole structure.
Exactly. And what's fascinating is that Hawkins believes that this hierarchical structure
Okay.
is not just about processing sensory information.
Okay.
It's also fundamental to how the brain makes predictions.
Okay, I'm intrigued.
Yeah.
How does the hierarchical structure contribute to prediction?
Well, imagine you're looking at a window.
Okay.
Your eyes might be focused on the latch, but you still know that the latch is part of a window,
Yeah.
which is part of a wall, which is part of a house.
Yeah.
Your brain is constantly predicting and confirming these nested relationships, using the hierarchical structure to understand how everything fits together.
So it's not just about recognizing individual objects.
Right.
It's about understanding the context,
Yes.
the relationships between things.
Exactly. And this ability to understand context
Okay.
to make predictions about how things relate to each other,
Yeah.
well, that is a crucial aspect of intelligence.
This is all so fascinating.
It is.
It's like peeling back the layers of an onion,
Yeah.
revealing more and more complexity and sophistication in how our brains work.
It's a truly amazing organ.
But I have to admit, my brain is starting to feel a little overloaded.
I understand.
Maybe it's time to take a break
Okay.
and let all this new information sink in.
Sounds good.
But before we do,
Yeah.
I have to say, I'm really starting to see how this memory prediction framework
Uh-huh.
really changes how we think about intelligence.
It's a game changer.
It is.
For sure.
So we'll take a break and then we'll come back and talk more about this.
Okay, sounds good.
Awesome.
Welcome back. Before the break, we were starting to talk about analogy
Oh, yeah. Analogy.
and how it plays a crucial role in how our brains learn and create.
You know, I'm really curious about this.
Uh-huh.
We often hear that analogy is important for creativity,
Yeah.
but I never really understood how it works in the brain.
Well, it's actually pretty simple,
Okay.
yet incredibly powerful.
Right.
Our brains are constantly searching for patterns,
Yeah.
for similarities between things.
Hmm.
When we encounter a new situation, Our
Yeah.
brains try to find a match in our memory,
Right.
something that we've experienced before that
Mhm.
might be analogous to this new situation.
Can you give me an example?
Sure, imagine you're trying to learn how to ride a bike.
Yeah.
It's a new skill,
Right.
something you've never done before, but your brain might draw an analogy to something you already know how to do,
Oh, okay.
like roller skating or skateboarding.
Mm.
You've already learned the basic principles of balance and coordination,
Right.
so you can apply those same principles to riding a bike.
That makes sense. It's like my brain is saying,
Right.
hey, this new thing is kind of like that old thing.
Yeah.
So maybe the same rules apply.
Exactly. And this process of analogical thinking isn't just for physical skills.
Oh, really?
It happens at all levels of thought. It's how we solve problems,
Okay.
come up with new ideas,
Hmm.
and even understand abstract concepts.
So when I'm struggling with a work problem
Yeah.
and suddenly remember a strategy I use to solve a similar problem in a completely different context,
Yeah,
that's my brain making an analogy.
that's right. Your brain is constantly searching for connections, for
Wow.
patterns that can help you understand the world and navigate new situations.
That's pretty amazing.
It is.
But it also seems like there's a lot of room for error.
That's true.
What if our brains make false analogies?
Yeah.
What if we see connections that aren't really there?
That's a great point.
Like, what about conspiracy theories?
Yeah.
Those seem like false analogies, right?
Exactly. False analogies are a real danger.
Okay.
They can lead us down some pretty wacky paths.
Right.
Think about some of the conspiracy theories that circulate online.
Yeah.
They often rely on false analogies,
Mm.
drawing connections between unrelated events
Okay.
and weaving them into elaborate narratives.
So it's like our brains are so good at finding patterns
Yeah,
that sometimes we find them even when they don't exist.
that's right. It's a double-edged sword.
Okay.
Our ability to make analogies is essential for learning, problem solving, and creativity.
Right.
But it also requires critical thinking
Yeah.
and a willingness to question our assumptions.
It's a good point.
We can't just blindly accept every connection our brains make,
I agree. We have to be discerning.
right?
So, okay, I'm starting to see how this all fits together.
Yeah.
Our brains are constantly predicting the future,
Uh-huh.
using memory and analogy to make sense of the world around us.
It's all connected.
But how does this relate to Hawkins' work on intelligent machines?
Well, Hawkins believes that understanding how the brain works
Okay.
is the key to building truly intelligent machines.
Mm.
He argues that if we want to create machines that can learn, adapt, and be creative,
Yeah.
we need to move beyond traditional computing
Okay.
and embrace this memory prediction framework.
So it's not about just building faster computers with more processing power.
No, it's not just about brute force.
It's about building machines that can learn and predict like our brains do.
Exactly. Hawkins isn't interested in replicating human behavior. He's interested in replicating the principles of intelligence itself.
Okay.
He believes that intelligent machines don't have to look like us
Right.
or even act like us,
Mm.
as long as they can learn, adapt, and make predictions based on their experiences.
So we could have intelligent machines that look like cars or building
Yeah.
or even just exist as software programs.
Exactly. The form factor doesn't matter as much as the underlying principles.
Interesting.
And Hawkins believes that the key to building these intelligent machines
Yeah.
is to understand how the neocortex,
Okay.
with its hierarchical structure
Right.
and memory prediction capabilities,
Yeah.
actually works.
So it's like we need to crack the code of the brain
Yeah, kind
before we can build truly intelligent machines.
We need to understand the blueprint.
That's exciting,
It is.
but it also seems like a daunting task.
Well, it's definitely a challenge.
Where do we even begin?
Hawkins suggests we start with the senses.
Okay.
Our intelligent machines need a way to perceive the world,
Hmm.
to extract information from their environment.
So just like we have eyes to see,
Yes.
ears to hear,
Yeah.
and skin to feel,
Exactly.
intelligent machines need sensors to gather information about the world.
Precisely. But these sensors don't have to be limited to human senses.
Well,
They could be designed to perceive things we can't,
like what?
like infrared radiation, magnetic fields, or even stock market trends.
So we could have machines that can see things we can't.
Yeah.
Or hear patterns in data that are invisible to humans.
Exactly. And just as our senses send information to our brains, these sensors would feed data into the machine's memory system.
And this memory system would be structured like the neocortex,
That's right.
with its hierarchical levels
Right.
and ability to store sequences, recognize invariant representations,
Yeah.
and make predictions.
That's the idea. But building a memory system that can rival the complexity and efficiency of the neocortex,
Yeah,
it's a huge challenge.
I can imagine.
We're talking about a system with trillions of connections,
Wow.
capable of storing vast amounts of information
Okay.
and processing it at lightning speed.
That's incredible. So it's not just about having enough storage space.
Right.
It's about having the right kind of connectivity,
Exactly.
the right kind of architecture that allows for rapid learning and prediction.
That's right. And this is where understanding the principles of the neocortex becomes crucial.
Right.
We need to figure out how information flows through the hierarchy, how invariant representations are formed,
Yeah.
and how the brain uses analogy to learn and create.
This sounds like we're talking about building a super brain here.
It's definitely a big challenge.
Are we aiming to create machines that are smarter than humans?
That's a question that raises both excitement and concern.
I bet.
Hawkins believes that it's possible to create machines that surpass human intelligence in certain areas.
Like what?
For example, imagine a machine that can analyze massive data sets of medical research
Okay.
and identify patterns that human scientists might miss.
That could revolutionize
Yeah.
medicine. But the idea of machines outsmarting us, even in specific areas,
Yeah.
it's a little unsettling, isn't it?
It's a valid concern.
Yeah.
But Hawkins believes that the potential benefits of intelligent machines
Okay.
far outweigh the risks. He argues that we need to be mindful of the potential dangers,
Right.
but that we shouldn't let fear hold us back from pursuing this incredible opportunity.
So it's like any powerful technology. It can be used for good or for evil.
Exactly.
The key is to ensure that these machines are aligned with our values
Right?
and that we have mechanisms in place to control their behavior.
Precisely. And Hawkins believes that the best way to ensure that intelligent machines are beneficial
Okay.
is to build them based on the principles of the human brain.
Hmm.
He argues that our brains are fundamentally creative and problem-solving organs,
Okay.
and that if we build machines that work like our brains,
Yeah.
they will be inherently beneficial to humanity.
That's a reassuring thought.
It is.
But even if we can overcome the technical challenges,
Yeah.
how do we even begin to train an intelligent machine?
Question.
Do we have to program them with all the knowledge and skills they need?
That's where the beauty of the neocortical algorithm comes in. Hawkins believes that if we can build a system that truly mimics the neocortex,
Yeah.
learning will be an emergent property.
What do you mean by that?
Well, just like a child learns through experience.
Right.
An intelligent machine could learn by interacting with its environment, receiving feedback, and constantly updating its memory prediction system.
So we wouldn't have to program it with specific knowledge.
Right.
It would learn on its own, just like we do.
That's the idea. Of course, we would need to guide its initial learning, much like we raise and educate children.
Right.
But the goal is to create a system that's capable of autonomous learning,
Wow.
constantly expanding its knowledge and abilities through experience.
That's both fascinating and a little mind-boggling.
It is. It's a really exciting prospect.
Okay, so let's imagine for a moment that we can actually achieve this.
Right.
What kind of world would it be like to live in a world with intelligent machines? What could they do?
The possibilities are truly limitless.
Give me some examples.
We could have self-driving cars that are not only safe, but can actually understand and predict the behavior of other drivers,
Wow.
making our roads safer than ever before.
That would be incredible. It would completely transform transportation.
It would.
What else can you envision?
We could have machines that can translate languages flawlessly,
Ooh.
capturing not just the words,
Okay.
but the nuances and cultural context of human speech.
That would break down so many barriers between people.
You would.
We could finally have real-time, cross-cultural communication
Right?
that feels natural and effortless.
Exactly. And it goes beyond just language translation.
Oh.
Imagine intelligent machines that can assist us in scientific discovery, analyzing vast amounts of data,
Okay.
and identifying patterns that would take human scientists decades to uncover.
It would be like having a tireless research assistant
Yeah.
that can help us make groundbreaking discoveries in medicine, energy, space exploration.
The possibilities are endless.
This is all incredibly exciting.
It is.
But I have to admit, part of me is still wondering,
What's that?
what about us? What happens to humans in a world with intelligent machines?
Yeah.
Do we become obsolete?
That's a question that many people are asking.
Right.
But Hawkins believes that the future is not about machines replacing humans,
Right.
but about humans and machines working together in new and innovative ways.
So it's about collaboration, not competition.
Exactly. Just as the invention of the computer didn't make humans obsolete,
Right.
the creation of intelligent machines won't replace us.
Okay.
Instead, it will augment our abilities, allowing us to do things we never thought possible.
That's a much more optimistic view. It's not about humans versus machines.
Right.
It's about humans and machines working together to create a better future.
Precisely. And Hawkins believes that this collaboration has the potential to unlock a new era of human progress.
Wow.
An era where we can solve the grand challenges facing our species and create a world that is more just, equitable, and sustainable.
This is all so inspiring. But before we get too carried away with visions of a utopian future, let's get back to the nitty-gritty of building these intelligent machines.
Right.
What are some of the specific challenges that we need to overcome?
Well, as we discussed earlier, building a memory system that can rival the complexity and efficiency of the neocortex, that's a major hurdle.
We're talking about trillions of connections.
Yeah, right.
How do we even begin to build something that complex?
It's a daunting task.
It is.
But Hawkins believes that it's not insurmountable.
Okay.
He points out that while the brain is incredibly complex,
Yeah.
it's also built from relatively simple components, neurons and synapses.
So it's like building a complex structure out of simple Lego bricks.
That's a good analogy. And just as we can build incredibly complex structures with Legos, we can potentially build a neocortex-like memory system using simple, scalable components.
But even if we can figure out the hardware, how do we program these intelligent machines? Do we need to manually code every single rule and instruction?
That's where Hawkins' memory prediction framework comes in. He believes that the key to intelligence is not explicit programming, but rather the ability to learn from experience.
Okay.
Just like a child learns through trial and error, an intelligent machine could learn by interacting with its environment and receiving feedback.
So instead of trying to program every possible scenario, we need to create machines that can learn and adapt on their own.
Exactly. And Hawkins believes that this learning process can be guided by a simple, elegant algorithm. An algorithm that captures the essence of how the neocortex learns and predicts.
Okay, this is all starting to make sense.
Good.
But there's still one big question that I can't shake.
What's that?
What about consciousness?
Ah, yes, the big one.
Can we build machines that are not only intelligent,
but
also conscious?
That's a question that has fascinated philosophers and scientists for centuries, and one that we'll explore in the final part of our deep dive.
Okay, I'm ready for it.
Stay tuned, because things are about to get even more mind-bending.
All right, we're back and ready to tackle the big one, consciousness.
The big one, yeah.
I have to admit, this is the part that really blows my mind.
I get it.
Can we really create machines that are not only intelligent, but also aware of themselves and the world around them?
It's a question that's both fascinating and a little daunting, right?
Sure.
For centuries, we've considered consciousness to be a uniquely human trait. You know, something that sets us apart from other animals and certainly machines. But as we delve deeper into the workings of the brain, that line starts to blur a bit.
Yeah, I can see that. You know, if our brains are just incredibly complex biological machines, and we're able to create machines that mimic those functions, isn't it possible that consciousness could emerge in those machines as well?
That's exactly the argument that Hawkins puts forward. He suggests that consciousness, you know, it isn't some mystical or spiritual force, but rather an emergent property of a sufficiently complex and interconnected system, like the human neocortex.
So it's not about adding some special ingredient to the mix.
No.
It's about creating the right conditions, the right architecture, and then consciousness just arises naturally.
That's the idea, Think about it like this. A single ant isn't particularly intelligent. But a colony of ants working together can exhibit incredibly complex and seemingly intelligent behavior. Similarly, a single neuron isn't conscious. But billions of neurons interconnected in the right way can give rise to the phenomenon we call consciousness.
That's a really interesting analogy.
It is.
So if we can build machines that have the same kind of complexity and interconnectedness as the human neocortex, we could potentially create conscious machines.
That's what Hawkins suggests, but of course it's still a theoretical possibility.
Right.
And we're a long way from being able to build machines with that level of sophistication.
Yeah, for sure.
But it is a tantalizing possibility.
It is.
And one that raises some profound ethical questions.
Absolutely. I mean, if we create machines that are conscious,
yeah,
do we have a responsibility to treat them differently than we treat other machines?
It's a big question.
Do they have rights?
Yeah, those are questions that we'll need to grapple with as we move forward in this field, you know.
Right.
It's important that we have these conversations now.
I agree. We need to be having these conversations.
Yeah, before the technology advances to the point where these questions become urgent.
Yeah. It's like we're entering a new frontier.
It is a new frontier.
And we need to be prepared for the challenges and the responsibilities that come with it.
For sure.
But let's shift gears a bit.
Okay.
And talk about some of the more concrete predictions that Hawkins makes about intelligent machines.
Okay.
He doesn't just theorize.
Yeah.
He actually lays out some specific things we should be looking for.
Okay.
As we explore the neocortex.
Right.
And try to build these machines.
Yeah, that's one of the things I admire most about Hawkins' work.
Oh, yeah.
He's not just a dreamer, he's a pragmatist.
Okay.
He wants to see his ideas tested and put into practice.
I like that. So what are some of these concrete predictions?
Whoa.
What should we be on the lookout for as we delve deeper into the brain?
One of his key predictions is that we should find anticipatory cells throughout the neocortex.
Anticipatory cell. Okay, remind me about this whole predicting the future thing again.
Sure. Remember how we talked about the brain constantly predicting the future?
Yeah.
Hawkins believes that there are specific neurons that become active in anticipation of a particular event.
So if I know that my phone is going to ring in 5 seconds, there are cells in my brain that are already firing in anticipation of that sound.
Exactly. And he suggests that these anticipatory cells aren't just randomly scattered throughout the brain. You know, their location in the cortical hierarchy depends on the specificity of the prediction.
So a vague prediction, like I'm going to hear a sound, might activate cells higher up in the hierarchy.
Right.
While a precise prediction, like I'm going to hear my phone's ringtone, might activate cells closer to the auditory cortex.
Precisely. The more precise the prediction, the further down the hierarchy the activity should flow.
Okay.
And this is something that can be tested experimentally.
Oh, really?
Yeah, scientists can design experiments to see if they can identify these anticipatory cells.
Okay.
And map their location in the brain.
That's really cool. It's like we can actually look inside the brain and see the prediction process in action.
It is pretty amazing.
What other predictions does Hawkins make?
Another fascinating prediction is that representations move down the hierarchy with training.
Can you explain what you mean by that?
Sure. It means that as we learn and become more familiar with something, the neural activity associated with it shifts to lower levels of the cortex.
So when I first learned to read, the act of recognizing letters might have activated areas higher up in the hierarchy.
Yeah.
But now, after years of practice, that same recognition happens at a lower level, closer to the visual cortex.
That's a great example. It's as if the brain becomes more efficient at processing familiar information.
Okay.
Delegating it to lower levels.
Right.
So that higher levels can focus on more complex tasks.
It suggests that learning isn't just about adding new information to our memory banks.
Right.
It's also about reorganizing our brain's structure.
Exactly.
To optimize processing.
It's a dynamic, constantly evolving system, not a static structure.
And this has important implications for building intelligent machines, right?
Absolutely. If we want machines that can learn and adapt like the human brain, we need to figure out how to replicate this hierarchical structure and this dynamic flow of information.
It's like we're trying to build a machine that can not only store information, but can also constantly reorganize itself to become more efficient and adaptable.
That's a great way to put it. And this brings us back to the importance of understanding how invariant representations are formed at each level of the hierarchy.
Right, because those invariant representations allow the brain to recognize things even when they change appearance.
Right.
Like seeing a friend's face from a different angle or in different lighting.
Exactly. And these invariant representations are formed through a process of learning and prediction.
Okay.
Constantly comparing sensory input to expectations based on past experiences.
Okay.
So if we want to build machines that can truly learn and adapt, we need to find ways to replicate this process.
It sounds like we're talking about building machines that can not only store information,
right,
but can also actively learn from their environment and refine their predictions over time.
That's the key. And Hawkins points out that this ability to learn and predict through analogy, as we discussed earlier, is not just essential for intelligence.
Oh, sure.
It's also the foundation of creativity.
Because creativity is all about making connections between seemingly unrelated ideas,
yes,
recognizing patterns, and applying knowledge from one domain to another.
Exactly. And this is something that computers, as they are traditionally programmed, are not very good at.
Yeah, that's true.
So if we want to build machines that can truly be creative,
okay,
we need to move beyond simple algorithms and data processing.
Right.
And find ways to replicate the neocortex's remarkable ability to learn and predict through analogy.
It's like we need to teach machines how to think outside the box, how to see connections that we might not even notice.
That's a great way to put it. And Hawkins believes that this is not just possible.
Okay.
It's essential for the future of humanity. He envisions a world where intelligent machines augment our own abilities, helping us solve complex problems, make better decisions, and even expand our understanding of the universe.
Wow, it's an incredible vision.
It is.
It's a bit overwhelming to think about all the possibilities and the challenges that lie ahead.
It's a lot to take in.
It is.
But I think Hawkins' work gives us a sense of hope and direction.
Okay.
He's shown us that intelligence isn't some magical quality.
Right.
It's a product of a specific kind of architecture, a kind of architecture that we can understand and potentially replicate.
That's a really empowering thought.
It is.
It means that we're not just passive observers of intelligence.
Right.
We can be active participants in its creation.
Exactly. And who knows what amazing things we might discover along the way.
Well, I think our brains have had enough exercise for one day.
I know mine has.
This has been an incredible journey, exploring the fascinating world of the brain and the potential of intelligent machines.
It really has.
Thanks for joining us on this deep dive into On Intelligence by Jeff Hawkins.
My pleasure.
It's a book that truly challenges us to rethink what it means to be intelligent and to imagine a future where humans and machines collaborate to create a world that is, well, smarter, more creative, and more compassionate.
I couldn't agree more.
If you want to explore these ideas further, we highly recommend checking out the book.
Definitely.
It's a mind-expanding read that will change the way you think about your own brain and the potential of intelligence.
It will change how you think about everything.
And who knows, maybe you'll even inspire you to build the next generation of intelligent machines.